Production and propagation of wave. Waves are one way in which energy may be transferred from one point to the other. So it's energy that is transferred but not matter. Mechanical waves need a medium to travel through. So as the name suggests, mechanical, so it needs a medium. Then we have the longitudinal waves. In this kind of waves, vibrations or oscillations are parallel to the direction of wave propagation. So the wave propagation is just how the wave is traveling. Then for the transverse waves, the vibrations are perpendicular to the direction of the wave propagation. A wave that moves from one point of medium to another is a progressive wave. Electromagnetic waves are waves that can transmit energy from a vacuum, and these waves are always transverse waves. Electromagnetic waves are always transverse waves. Now let's talk about part of a wave. So we have a wave here. So we have a wave-like motion, as you can see. This is a wave-like motion. This point here is called the rest position. Then we also have the wavelength. So the distance from this point to this point, or from this point to this point, or from this point to this point is the wavelength. The peak over here is the maximum point on the wave. So the maximum point that the maximum point that the wave can reach is the peak. Then we have the trough over here, which is the minimum. Then we can talk of the amplitude, the distance from the midline to the peak is called the amplitude. Then we can talk of the period. So the period is the interval within which the cycle of the wave repeats. So from this point to this point is one period, because the pattern of the wave within this period is the same as the pattern within this period. That is from here to here, and the same as from here to here. So it is having the same pattern throughout. So that is what we call period. So this is a periodic wave or a sinusoid. Now let's talk about wave speed. The speed of a wave can be calculated by multiplying the frequency of the wave by the wavelength. So mathematically it is V equal F times lambda. So the frequency is F and wavelength is lambda. So in this case, the wave speed V is measured in meters per second. Then also the frequency F is measured in hertz. Then we have the wavelength, which is lambda measured in meters. Now let's talk about a general equation for the wave. The general equation of the wave in terms of x and t is given by y equal a sine kx minus omega t plus phi. So y here is the displacement of the wave. Then the k is given by 2 pi over lambda, which is the wavelength constant. Then we have the omega, which is given by 2 pi times the frequency of the wave. Now we can use these equations to do a simple calculation. So the first example here is WASSCE NOVDEC 2011. The displacement of a plane progressive wave is given by the equation y equal 12.5 sine 240 pi t minus 0.5 pi x, where the symbols have their usual meanings. Y and x are in meters and t in seconds. For the wave, determine I the frequency, I the wavelength, then I the speed. To start solving this question, we need to write down the general wave equation that we saw, and this is given by y is equal to a sine kx minus omega t plus phi. Now we compare this to the equation given to us, which is y is equal to 12.5 sine 240 pi t 240 pi t minus 0.50 pi x. When we do that comparison, we can see that A will be equal to 12.5, then k will be equal to 0.5, and omega will be equal to 240 pi. So this implies that our amplitude is 12.5. Then we have the k, the wave number, to be equal to 0.5 pi. Then we have the angular speed to be equal to 240 pi. Now let's use the relation omega is equal to 2 pi times the frequency. We can solve for the frequency to obtain omega over 2 pi. Let us do the substitution to get omega is 240 pi over 2 pi. And when we simplify this, you can get, if you simplify this, you get 120 hertz. 120 hertz. So the speed is 120 hertz. Now let's calculate the wavelength. The wavelength is given by lambda is equal to 2 pi over k. So from the equation, we know the value of k to be 0.5 pi. So let's do the substitution into the formula to get lambda, which is the wavelength, to be equal to 2 pi over 0.5 pi. So that will give us 4 meters. Note that negative sign is just showing the direction of the wave. Now let's come to the third one, the speed. So the speed is given by v is equal to f times lambda, that is frequency times the wavelength. So like we saw, the frequency was 120 hertz and the lambda, which is the wavelength, was 4 meters. So therefore the speed will be equal to 4 times 120, which is 480 meters per second. So we have this over here. We want to find out which of the following equations does not represent a traveling wave. So like we saw, the general equation of the traveling wave is given by y is equal to a sine kx minus omega t plus phi. So we need to compare all of these equations to the general one. So now let's put k equals 0. Let's put k equals 0 into this equation to get y is equal to a sine negative omega t plus phi. Negative omega t plus phi. So we can see that the phi is corresponding to the theta and the negative omega to the omega. So the two equations are identical. They are all traveling waves, just that they are traveling in the opposite direction, as we can see. So they are, therefore the A represents the equation of a traveling wave. Now let's look at the second part. The second part, which is the B, we have y is equal to a sine 2 pi t over capital T minus x over lambda. So we need to expand. To get 2 pi t over capital T times, so 2 pi over capital T, not small t. So 2 pi over capital T times t, then we have minus 2 pi over lambda times x. So note that we can rewrite this as 1 over t, and that 1 over t is the frequency. 1 over capital T is the frequency, times 2 pi, then times t, minus, note that 2 pi over lambda is equal to k. From that equation, k is equal to 2 pi, lambda from the equation lambda equal to 2 pi over k. We get that when we solve for k. Now this becomes 2 pi times frequency times t minus kx. But we know that 2 pi times frequency is the angular speed, which is frequency, which is omega. So it becomes omega t minus kx. So this is an equation of a wave with the phase shift being 0. Now we come to the third one. We can see clearly that we cannot rewrite this in terms of the general equation. So C is not an equation of a traveling wave. So that will be the correct answer. But now let's look at the D part 2 and show that it can also represent the equation of a traveling wave. The equation is y equal a sine 2 pi over lambda times lambda f. You know the v, the speed is the lambda f, times t. So lambda f times t minus 2 pi over lambda times x. But note that 2 pi over lambda, so the lambdas will cancel. When the lambdas cancel, we are left with 2 pi times f over there. So when the lambdas cancel, we are left with 2 pi times f. And you know what that will give us? You know why? That will give us omega. So we have 2 pi f 2 pi f 2 pi f times t 2 pi f times t minus kx, because 2 pi over lambda is k. So y will be equal to a sine omega t minus kx.